Hello, this is Anthony Engel. I hope you find this topic review helpful as you prepare for the engineering exam. We set up a sample problem for differential leveling, working from the benchmark at the top of this hillside and going to set a temporary benchmark in the base of this oak tree, and then to complete a level circuit by running the level back up the hill in order to close on our starting point, thus creating a loop down and back up. So these are our notes for a closed leveling circuit. The arrows provided are meant to help define the workflow. For example, we start at the benchmark with a known elevation and add to that a backside on that benchmark. That provides us with a height of instrument, the HI. From there we turn to perform a foresight. This time looking downhill, we see the rod height of 8.37. If we subtract that from the height of instrument, that would provide us with the ground elevation at that point. And so from ground at any point, that ground elevation, we will add the back sight. So we sometimes put a plus at that top of that column of back sight, because all these will be added to the elevation of our instrument. Add that back sight to provide you with the next height of instrument, and then the column for foresights going forward from there is always going to be a negative. So each time that the height of instrument is established, we subtract the foresight in order to produce the ground elevation at the next point. So we get ground elevation, right? We add the back sight, and that gives us the height of instrument. And then we subtract the next foresight, and that gives us the next ground elevation. So from here, elevation, add a back sight, that gives us height of instrument, and then subtract a foresight would give us ground elevation at the next point. Next point we'll add, gives us height of instrument, subtract, gives us the benchmark elevation. So this benchmark elevation, the benchmark at the base of the oak tree, based on that last foresight of 8.71 feet, is going to have an elevation of 2019.44. So this established benchmark elevation is determined to be 2019.44 initially. However, we have a potential problem in errors because we've only made the trek from the top of the hill to the bottom of the hill. So our level loop is not closed. It's not complete. So we need to perform the calculations and readings to take ourselves back to the top of the hill to close this level circuit. And then we'll see if we have any errors. And if there are, then those errors or adjustments would apply to each of the successive instrument setups. So every time that we moved that tripod, we're going to have to distribute some errors that may occur in trying to close this level loop, right? Otherwise, we hope we can get to the top of the hill and our surveyed elevation matches our initial elevation, and we would have no error. So again, let's see what it takes to go back up the hill, right? From our benchmark elevation, we set up the instrument and take a back sight on the benchmark, so that becomes a plus in the column and gives us our height of instrument. From there, subtract the foresight, gives us the elevation of ground. Go through this one more time. We add the backsight, gives us height of instrument, subtract the foresight, gives us ground, and then one yet more time, we add and then subtract, gives us height of ground. At this point, I make the comparison, right? I came back to the benchmark and my calculated elevation is 2053.21. So I, however, know that I'm supposed to be at 2053.18. So I have 3/100ths of a foot in this case of error that needs to be distributed. Some place along there, or maybe multiple places along that route, I must have carried the instrument an error. And another way to check for this error is to make a summation of these two columns. The summation of the backsights and the summation of the foresights. Right? So all of my backsights and all of my foresights, they should balance out. The difference between those is the difference between my starting elevation and my ending elevation. And so this indicates to us the amount of error being 0.03 feet, or 3/100ths of a foot. Here's the completed table with a check. If I take my starting elevation and I add all of the backsights, and then I take that and I subtract all of the foresights, then I should get my ending elevation, right? So that confirms that all of the backsights and foresights were applied from the starting elevation. Sort of could help to proof all of the values in between. So we must adjust this error, 3/100ths of a foot, and we're going to distribute that amongst the number of times that we set up that instrument, right? And so you can tell this by looking at how many times did I move the instrument, the HI. I have 1, 2, 3, 4, 5, 6, 7 setups. 7 times I had positioned or repositioned the instrument, and those are going to inherit this error adjustment. So I'm above by 3/100ths, which means I'm going to subtract the adjustment factor from each of those instrument setups. I'm going to make a subtraction on each of those to make that adjustment all the way through. So I'm going to distribute that 3/100ths over 7. That gives me an adjustment of 4/1000ths of a foot, 0.004 feet for each HI. So if I look at the first height of instrument and I in order to adjust the elevation, I would subtract 4/1000ths from this number. All right, and that would actually give me no change in the number. Right. Now at the next HI, I'm going to subtract that error resolution or adjustment twice. Right. Once the first time, once the second time. So I'll subtract 0.008, and that makes my adjusted elevation basically 100th place less than my original. We can go again to the next HI, subtract that error once, twice, 3 times. So that would be subtracting 0.012 away from the observed elevation, gives me the adjusted elevation. finally, at the last instrument setup, I subtract the adjustment factor for the error, 0.04, 7 times, or effectively subtracting 0.03 from the observed in order to get a adjusted elevation that makes that level circuit closed. Because now my adjusted elevation is equal to my starting elevation, which is a benchmark. So this adjustment in the adjusted elevation did in fact modify my benchmark as I originally had calculated it to be 2019.44. The adjusted elevation is 2019.42. Go into an example for profile leveling. In this case, instead of a closed circuit loop leveling, we're essentially venturing out along the path of a route in which we're establishing the existing ground or the profile of the ground. And so we're going to set up the instrument, but for efficiency, we're going to take many shots perhaps in the back sight and many shots in the foresight before we reach a turning point. Right? And from that turning point, we'll set up the instrument at another location and take several shots with notation to that turning point, but forwards and backwards, and then proceed as this route continues. Now this is still can be considered a closed loop if we tie on another benchmark. So here we have a benchmark elevation at the starting point of this survey that we tie to, record these back sights and foresights and so forth, and then at the end of this we do complete the leveling circuit because we tie into another benchmark that has been stored for the project. So if everything that we surveyed in between can be closed by understanding where we should have been in an ending elevation and what we started with our beginning elevation. So what we can do is take these survey shots into our notes, right? And so I have an example with different numbers here, but a blank sheet that we can use as a sample problem. And in this sheet, I've highlighted the areas that are blanks, and they are color coded so that we can go through this faster. So we have a benchmark starting elevation, right? We add the back sights, that's highlighted, and so we add 2, gives us the height of instrument, and then we proceed to subtract these rod readings. And in this case, rod reading and foresight, they actually could go in the same column, but it's simpler when we're doing profiling to sort of separate all those rod readings from the foresight, which was really used to establish the next turning point. That's why it's on this part of the column. If they're all in the same column, then the known information is that the turning point is the next elevation that really matters when we want to establish the next HI, or the next height of instrument. So these ones in between, we simply go through and subtract 7 from 355.6, or 6.2 from 355.6, or 9.4 from. So we're always, all of these are subtracting away from that height of instrument. Just the same, 12.1 is subtracted from the height of instrument to give us the elevation at that turning point. So if this is ground elevation at the turning point, then I add the back sight to establish my height of instrument. And then I can subtract each of those rod readings to give me the elevation of ground at all of those intermediate rod readings, and the furthest distance, likely the rod reading to my next turning point, is going to be subtracted from my height of instrument to give me the ground at that turning point. One more time through then, this ground elevation, add the backside gives me the height of instrument, and then I can subtract a foresight and another foresight and another foresight. Each time, whether it's a foresight or a rod reading, these are each getting subtracted from the height of instrument to give ground elevation at that location. So here is a clean version of the profile survey notes. Now this is an incomplete set of survey notes in that it doesn't come back to a finished benchmark, so it's not closed, and there haven't been any adjustments made otherwise for those elevations. The ability to directly use and interpret zenith angles comes into play, in particular when we're measuring distances that are on an incline. So here I have a total station instrument set up on the tripod here at the top of this hill, and I'm shooting to a prism or target that's at an incline, right? And my total station instrument will give me the reading L, the distance separating my instrument from that target. And it also gives me the measured zenith, right? So that's the angle from directly vertical to the direction of the line L. From there, we can apply simple trigonometry to solve for the distance x being a horizontal distance as L times the sine of the zenith angle, and the distance y being the vertical distance, being L cosine of the zenith angle. And the zenith angle is directly inputted. Whether the number varies from 0 to 180 degrees, the sine and cosine function sort of take care of that switchover from having a positive y to a negative y. Let's do an example problem. Let's say I'm positioned my instrument here at the bottom of Spartan Stadium, right? And I'm shooting towards a target or a prism up at the top row in the stadium bleachers, right? And so from there I directly read the zenith angle as being the incline from zenith 0 degrees directly north or directly up to the prism, and I get a 50-degree angle, right? And I also output the distance L, and that distance is 180 feet. So using the function to determine the horizontal distance, L times the sine of the zenith angle would be 180, the length along that hypotenuse side of a triangle, times the sine of 50. That gives me a horizontal distance of 138 feet. Now, just as a proof of concept, we could set this up in reverse. Say that I set my total station instrument up on the top row of the bleachers, and I shoot down towards a target that's at the bottom row of the bleachers on the field. And so my zenith angle in that case would be measured from directly vertical at 0 down to the target, which would be a 130-degree zenith angle. Now, of course, by the triangles involved, we could even prove the horizontal angle is going to be negative 40 degrees, or a 40-degree angle of depression, just by the triangles involved. So I set up the equation that the horizontal distance is equal to L times the sine of the zenith angle. So 180 times the sine of 30, 130 gives me a horizontal distance of 138. Exactly the same solution. Next, let's look at a distance problem. In this case, we're given a situation where point A is on the west side of the bridge at station 10 plus 0, 0. The bridge itself is 400 feet long to point B. A total electronic station is set up on point A and initially sighted at point B. Then a reflector is sighted at point O. So the TES turns an angle from B to O, and that angle is read out as 47 degrees 30 minutes and 45 seconds. The distance to that reflector from A to O is 388.22 feet. So from here we'll determine the station and offset of point O. I've labeled the station at point A as 10 plus 0, 0, and I know the station at point B is 14 plus 0, 0, since it's 14 feet ahead from point A. What I'm going to use is angle and distance to determine the station and offset. So we have our equation for sine and cosine, right? In this case, the adjacent side, right, using that angle theta, will give me the distance along the alignment. And the opposite side will give me the offset away from the alignment. So the station and offset away from the alignment of this bridge. If I evaluate first for the offset, I can rearrange the sine equation so that I compute for the opposite side equal to the hypotenuse times the sine of theta. So I'll input the hypotenuse, which is the distance that was shot or read to the prism, times the sine of that angle that was turned, gives me 286.28 feet, right? And pretty directly that is the offset. However, the offset, we should also be aware that the offset will have a direction. In this case, it's 286.28 feet to the right. If I'm looking in the forward direction from A to B, the direction of increasing stations, then this point O is offset to the right. Next, I'll rearrange the cosine equation to determine the adjacent leg of this triangle. So the hypotenuse times the cosine of that angle. I have the distance shot to the prism or reflector, 388.22 times the cosine of that angle gives me a distance of 262.22 feet. Right? So that's a distance away from point A, which is at station 10 plus 0, 0. So the station of my point O would be 262.22 feet further from point A. So it comes out to station 1262.22. Next, we can do a sample problem here on how to determine that cross-sectional area, also known as an end area. So we have an existing ground line in green that would be produced by providing or performing a survey of the existing ground. And then we have a proposed shape in blue, which would be the finished surface of the, in this case, the embankment for a highway. And so we also have the coordinates or position as it is with respect to the center line, right? And the CL in the middle is the center of the roadway, right? And so our coordinates go some to the left, it's in a negative direction, and some to the right, that's in a positive direction. And then with respect to elevation, they are all above the datum elevation of 0, right? And so we're using elevation 0 here as a relative measure of the height above that ground elevation. These elevations could be any value. For example, in our range of the Earth, within mid-Michigan, we might be at areas that are 600, 700, or 800 feet above mean sea level elevation. So in order to perform this calculation, I've given you kind of this slide as a blank template so that you can follow along. But we're going to use the method of coordinates to determine the area of this fill. And so I'm going to log these coordinates into the table to help with showing my calculation. I'm going to start from the westernmost point. I'll call that point A. And then I'm going to work my way sort of clockwise around this shape to B, C, D, and E. So I input the X position of point A, that's negative 18, and the Y position of point A, that's 8. Then I look at the line from A to B, right? So this line from A to B, and I input the X coordinate of point B, which is negative 10, and the Y coordinate, which is 10. And I'll go ahead and fill this out for lines BC, and then C to D, and D to E, and then finally from E back to A in order to close that shape. Here you can see that I've filled out the table with the coordinates x1s and x2s, y1s and y2s. Then I compute the change in x. Simply the x2 position subtract the x1 position. So this is my change in the x direction. And then I compute my average y position. So y1 plus y2 divided by 2. And from there, I take the change in x multiplied by the average y to get an area for that shape. So my difference in x's would be negative 10 minus negative 18, which is a positive 8. From there, my y average would be 8 plus 10, that's 18 divided by 2. The average is 9. So I fill out these columns, and then I do the computation of 8 times 9 is 72, 20 times 10 is 200, 10 times 8 is 80, negative 18 times 3 is negative 54, negative 20 times 4 is a negative 80. If I take the summation of all those areas, it gives me the area of the enclosed shape, in this case 218 square feet. Let's try this using the double meridian distance method, right? So the double meridian distance method is going to use the same shape, and we should get the same area, right? In this case, we're going to identify some points. I'm going to use the points A and B and C and D and E, sort of labeling those points in clockwise around the shape. Double meridian distance method relies on establishing essentially a meridian. The most convenient location for the meridian should be located on the passing through the westernmost point. So this will be my meridian. That way my distances can all be measured away from that meridian. Likewise, I want to set up a baseline, and the most convenient location for a baseline will be passing through the southernmost point. That way my departures can be measured from my meridian and my latitudes from my baseline. We're going to go ahead and define the line segments that complete this shape. So the first segment would be from A to B, next segment would be from B to C, and then C to D, and then D to E, and then to close it off we would go from E back to A, right? In the double meridian distance method, we evaluate the latitude and departure of each of these line segments. So the latitude from point A to point B is going to change in y direction by 2. The departure changes in x direction by 8. right? If I go from B to C, latitude changed by 0, departure changed by 20. If I go from C to D, latitude changed by -4, departure changed by 10. From D to E, latitude changed by -6, departure changed by -18. From E to A, latitude changed by 8, departure changed by -20. Next, we'll do the double meridian distance, DMD. Double meridian distance of the first line segment is equal to the departure, 8. Double meridian distance of the line segment BC is equal to the previous DMD plus the departure of the previous line plus the departure of the current line. So 8 plus 8 plus 20, that gives me 36. Double meridian distance of line segment C to D would be 36 plus 20 plus 10, that gives me 66. DMD of line DE, 66 plus 10 plus -18 gives me 58. And the DMD of the line segment from E to A is 58 plus -18 plus -20 gives me 20. And here's a check that my last DMD is the opposite of my last departure. Now I'll compute the double area, where the double area is equal to the DMD multiplied by the latitude. So 8 times 2 is 16, 36 times 0 is 0, 66 times -4 is -264, 58 times -6 is -348, and 20 times 8 is 160. If I sum this column, I get the summation of the double areas is equal to -436. That's the sum of the double areas. My actual area is equal to the summation of the double areas divided by 2. I'm going to take the absolute value. Because of the direction that I went, I get a negative. If I would have gone counterclockwise, I would have got a positive. And this gives me an area equal to 218 square feet. In order to estimate the volume, we can take use of the average end area method. This is probably the most practical for use on linear type of facilities, such as highways or railways. We take two different end areas, one at the beginning, A1, one at the end, A2. We average those two areas and then multiply by the length that separates them in order to give us an estimate of the volume of the shape that's enclosed. So here's the formulation. Average end area is assembled as A1 plus A2 divided by 2, multiplied by the length between those areas, gives us the volume that's involved. We can do a brief example problem. Let's say that area number 1 is 400 square feet, and area number 2 is 218 square feet, and that these are separated by 120 feet apart. Right? So I would be able to compute my volume as being equal to the average area, end area, so 400 plus 218 divided by 2, and then multiplied by the length, 120, gives me a volume in cubic feet of 37,080 cubic feet. So for earthwork projects, when planning or estimating, it's often necessary to Find the volume of material that would be excavated or placed as fill. The procedures can be divided into three principal steps or categories. One is a pit excavation. This is a relatively small, deep excavation required for basements or foundations. Another is a trench type of excavation, usually long in length, linear, such as for utility lines, drainage ditches. And then excavating really large areas, right? So three different types of excavation. Let's look first at an example for a pit excavation. Here we have a basement area that's 30 feet on one side and 25 feet on the other in size. Depth of excavation is indicated here in feet with the metric dimensions in parentheses. So this is the depth of excavation at each of those corners, from the existing surface to the finished floor or the bottom of the basement. Treating this like a pit excavation, we can compute the volume in blue here of just that rectangular shape. But we must also identify the volume that's outside of that rectangular shape in order to excavate for that basement. Let's look at this as a picture example. We're trying to achieve a finished excavation here for the basement, but it's not just the physical corners of the building. We must also excavate beyond the edges of the building in order to have some working space for placement of those foundations, and in order for that soil slopes to rest at that angle of repose in order for it to be safe. Michigan OSHA provides an allowable angle of repose for different soil types. For a solid rock, the angle of repose could theoretically be 90 degrees, sort of vertical. But for other soil types, that angle of repose will naturally be flatter and flatter. If we use for this example a dry sand, we see that a dry sand has an angle of repose, a safe angle of repose, as a 1-on-1 or 45-degree slope. This is in regards to the safety of that excavation. So we'll treat this excavation as a pit excavation, and we're going to use the average depth method. Right? So looking at the depth of excavation at these four corners, we get the average depth and determine the volume based upon that information. We take the surface cross-sectional, or the surface area, 25 feet by 30 feet. That gives me a surface area of 750 square feet. The average depth is based upon those four corners of the excavation, right? Averaging those four corners gives me an average depth of 6.9 feet. So my computed volume in that shape is my surface area, 750 multiplied by the average depth, 6.9. If I convert that from cubic feet to cubic yards, I can divide by 27, and that gives me about 192 cubic yards in a bank condition, existing soil. Now recall that we need to over-excavate beyond the physical size of that structure. We need to over-excavate to lay those slopes back for safety, right? So if those slopes are laid back at a 1-on-1 or a 45-degree angle, let's estimate the volume of excavation that's in addition to just the basement area. I'm also looking to provide about 2 feet of working space for the construction of the foundation. So not just the wall sort of directly, but 2 feet beyond the exterior of the wall in order to provide some working space to build that wall foundation. And then from there going at a 1-on-1 or a 45-degree angle. So we're going to over excavate this triangular shape, right, parallel to all of the edges of the rectangle, right? So that'd be this green highlighted area. And the volume of that highlighted area in green can be considered as a trapezoid, right? So we'll use the area of a trapezoid in order to determine that cross-sectional area and then apply it around the perimeter of that shape. So the cross-sectional area of this trapezoid is 38.5 square feet. If I multiply by the perimeter of that shape, 30 feet on two sides and 25 feet on two sides, then I come up with 157 cubic yards of excavation in order to accomplish those parts that are parallel to the walls. Then we need to estimate the volume that's included in the corners. Those are highlighted here in blue. So the corners we're going to treat like a conical shape or a cone. The radius of this cone is 9 feet, right? That's the dimension that we're over excavating, 2 feet plus another 7 feet per the depth gives us a 9-foot cone. Base is equal to pi r squared. So the volume is 1/3 of the base times the height. So I get a volume in that cone of 22 cubic yards. Add the green 157 to the blue 22 and the red 192 gives me a total excavation of 371 cubic yards. So in summary, approximately 179 bank cubic yards of excavation is added to what would otherwise be the basement area in order to satisfy the angle of repose that's required by the safety standards. That's almost double the original excavation volume for just the basement itself in order to safely construct this facility. Next, let's look at an example for much larger areas of excavation. In this case, going along with the idea of an average depth, but not using just 4 corners to estimate that depth, but using depth based on a weighting factor. And so the weighting factor applies to interior points, edges, and corners. At every interior point, an interior point has 4 intersecting legs. That interior point is given a scale or a weighting factor of multiplied times 4 when computing the average depth. An exterior point, on the other hand, for example, is along the edges, right? And so that exterior point has 3 intersecting edges, is given a weighting factor of times 2. And then finally, a corner, which exists at the intersection of 2 lines, that corner point is given a weighting factor of times 1. So as an example, look at these depths from the existing ground surface to the finished excavation, bottom of the basement. This is how much we need to cut or dig away at each of these points for a relatively large area. The volume of excavation required, we can compute the average depth. And that average depth is going to be the sum of the product of depth times their weighting factor divided by the sum of all of the weights. So first we might look at the corners. I have 4 corners, and at those corners my depths are 6 feet, 3.4 feet, 2 feet, and 4 feet. Then I look at the perimeter, the borders. So those border or perimeter depths are around the perimeter, these exterior border points. Then we use the interior points. Next we apply the weighting factors. So our total area is the length times width, but the volume is weighted based upon the average depth. And that average depth uses the sum of the corner points times a weighting factor of 1 plus the sum of the border points, those are in green here, multiplied by a weighting factor of 2, and then the sum of the interior points, that's in blue here, multiplied by a weighting factor of 4. This is divided then by the sum of all of the weighting factors, or the sum of the weights, right? And so here we get an average depth of 4.3 feet. Multiply the area by the average depth, and we get a computed volume for this large area. So there's a traversing example. It's a four-sided traverse. You can see the measured angles. And so if we sum all of the interior angles, we sum all those interior angles, come up with 360 degrees and 40 minutes. Well, that just happens to be 40 minutes too large, because a four-sided shape should only have 360 degrees of interior angles. So what am I going to do with those extra 40 minutes? Right? I have four traverse corners, right? Four sides, four corners, so I'm going to reduce each of those measured angles by distributing that error of, say, 40 minutes across four different traverse points or corners. So 40 divided by 4, I'm going to subtract 10 minutes from each, right? And so what that does is that effectively here adjusts the interior angles. That's the first step of closing the traverse. From there we go to essentially compute the azimuths of each of the courses, right? It could be the bearing or the azimuth. Both of those is saying it's the angle of that line. So in this case, the line from A to Z, or A to B, line from point A to B has an azimuth that can be calculated, right? That was the initial shot, and then the azimuth to the next point along that shape, which is from B to C. It takes the interior angle that was read, right, adds it to the azimuth of the prior line, and we get the azimuth of the line from B to C. So compute each of those courses, right? From there we go into calculate latitudes and departures, right? That's the third step of closing the traverse. And so this is best done or organized in a table. So we got points A, B, C, and D, and we're describing lines that connect each point, and we had previously just calculated the azimuth of each of those lines. We have the measured distance, which was recorded during the survey of each of those legs of the traverse. And from there we compute, and this is the part that we're computing, is the latitudes and departures. So we compute each of the latitudes and departures, and each latitude is a difference in the north, and each departure is a difference in the east. So we can use latitudes and departures as well as our given or assumed coordinates at our starting point. And so each of the northing, if I add the latitude, I would get the next northing, right? Or each of the easting, if I add the departure, whether it be a positive or a negative, would give me the easting of the next point. From there we compute linear misclosure, right? And so essentially we should have been at our original, our starting point, but our calculated position might be A prime. So what's the absolute difference between those is delta and y's squared plus a delta and x squared under the square root. That gives me 4.69 feet in linear misclosure. Then the question is that acceptable according to our survey? What's that relative precision? So if I take that divided by the total length of the traverse, right? The summation of the perimeter of that traverse, and so that gives me a linear misclosure or a relative position, and I can use that to decide if the survey needs to be reperformed, or if I can just go ahead and correct for the errors and close the traverse myself. So that's step number 4, and then step number 5, we correct the latitudes and departures. All right, so I take an existing latitude of, say, line from A to B, and I'm correcting it by multiplying by a correction factor that is, it's a range to adjust for the error. So what I know is that my errors of latitude in total was 2.37. My errors of departure in total was 4.05. Where I get that is the difference between A and A prime, 2.37 in latitude and 4.05 in departure. What I essentially used to compute linear misclosure. And so I also know the total perimeter of this traverse, and I know the length of this first side. So that side from line segment from A to B is 430 feet long as it was directly measured, and the total traverse should be 1528. So I'm just proportioning my error in latitude across this particular line segment as a proportion is to the length of that line segment divided by the total perimeter, or the length of the entire shape. So I do the same thing for departures. I take a departure at AB. I need to make a correction in total of 4.05 feet in this whole traverse, and I'm going to use or prorate proportion that according to the length of that side divided by the perimeter of the traverse. So that gives me the adjustment for each of those latitudes and departures. So we kind of go through all of those and adjust the coordinates of every point around that traverse. Recalculate the length of each of those lines. And so I thought that the direct readout or measurement was 430 feet, but after I correct or close this traverse, I get 428.7 feet as the length of the line from A to B. Right. Continue doing that with each of the other lines, and what you would effectively do is close the traverse by bringing the end point into coincidence with the starting point. So corrected latitudes and departures are provided in this table, and then the confirmation is that if I go through and sum up from the adjusted start point, if I add each of the latitudes to the northing and I add each of the departures to the easting, I can go around the points of the traverse and come back to the precise starting point, so that I've effectively taken out any error between the starting and ending point. Closing a traverse is definitely a time-consuming and iterative process. Here's another example problem of calculating distances and azimuths in order to do traverse calculations. And so here you have a blank version of the given information. All right, so a site on an assumed meridian, turning, shooting to point B, relocating the instrument to point B, sighting back to point A, turning and sighting towards point C. And so we have the measured lengths along the course of these two legs of a traverse here. And so the first question is, what's the azimuth of the line from A to B? And that azimuth can be computed because we have an angle from what was an assumed east and west meridian. So sighting on perhaps two property corners, an east and west assumed meridian, turning a distance to the right, and so computing what azimuth is point A to, or the line from A to B in. We can see that the quadrant it is in the circle is very close to north, but it's west from the north and south line. So if I add 270 to kind of get us in the right quadrant, and then add the angle that was observed, one is 86 degrees, that gives me the azimuth of the line being 356 degrees and 29 minutes 58 seconds. Then we compute the latitude that's involved, the change in y, delta y. The length was recorded as part of the shot to the prism, right? So that's our horizontal length, and then we use the azimuth, which we have just calculated. That's my alpha in this equation, and so L cosine of alpha gives me the latitude that it would be encountered traveling from point A to point B. Likewise, I can calculate the departure. Departure is a delta in the x's direction, right? So L times the sine of the azimuth, or the alpha, that gives me the departure. And this says it's at negative 34.00 feet. So that means distance towards the west in a negative direction of departure. If I have an assumed northing and easting of point A, our assumed coordinates is 0, 0, then I can track the new coordinates of point B by adding the latitude to the northing and adding the departure to the easting. So here I've computed the coordinates of point B using the latitudes and departures. Now I look and I turn an angle in sight to point C. Right, I have a measured distance and as well as a recorded angle to the right. So what's the azimuth of that line from point B to point C? That can be computed by taking the azimuth of my prior line, right, and then adding the angle that I turned to the right in order to get me to the line from B to C. So that gives me 543 degrees. Right? So I'll proceed to take away 180 a couple times here until it gets me in the correct location of my line, which is saying that the azimuth of that line from B to C is at 3 degrees and 32 minutes 35 seconds away from north, that azimuth being measured from north. So then I proceed to calculate my latitude and departure by using the length of the line and the azimuth that I've computed. So I get a latitude of another 552.7 feet going towards the north and a departure of 34.2 feet. It's a positive this time, so that means it was going towards the east. So when I add the latitude to the prior y coordinate, that gives me the coordinate of the y location, or the northing of point C. And if I add the departure to the prior x coordinate, then that gives me, or the x coordinate of point C. This is a summation of all the calculation, or sort of the final solution. Here is another challenge problem. Recall in the last problem that we established the coordinates of this property line, a partial of this traverse from point A to point C. Now consider that we've identified another line, perhaps by surveyed points on a utility structure, points D and point E. We want to find the coordinate where these lines cross. In order to do this, consider the formulation of each of these lines. Y equals ax plus b, where a is the slope of the line, delta y over delta x, and b is the intercept. The line equation for y1 is simplified because the origin coordinate is 0, 0. So there's no intercept term. The line equation for y2 is written as the slope, that is change in y values divided by change in x values, multiplied by an unknown variable x, and adding an intercept b. In order to solve for the intercept b, we can evaluate the y2 equation at point D. So y2 is the y-coordinate of 341 multiplied by the slope and the x-coordinate at point D. We can utilize this to solve for the intercept, which is where x equals to 0, and have a good definition of the line y2. Noting that the first line y1 is nearly north and south, The intercept would be a close approximation, in fact, of where these two lines cross. However, the proper way to do this will be to set the two lines, y1 and y2, equal to each other, and then solve for the x position where those two lines cross. So this can be written as the y1 equation equal to the y2 equation, and essentially rearrange this to solve for x. Here I've carried an extra decimal place just to highlight the importance of accuracy. In general, do not apply rounding until you've completed all of the calculations. This way you don't introduce an error simply by applying rounding too soon. Now we can evaluate either of these two equations, y1 or y2, to solve for the y position when x is equal to 0.043. You'll again see a small difference in the outcome, which really highlights the sensitivity to the number of decimal places. Ultimately, the point where these two lines cross is at 238.53 north and 0.04 east.